Friends, as early as 1831, Michael Faraday announced the concept of electromagnetic induction. In his experiment, he used a permanent bar magnet and an insulated coil of conducting material, say of N turns, and a current sensing galvanometer as shown. Permanent magnet and the coil are kept in the neighborhood of each other. A current sensing galvanometer is connected across the coil as shown in figure. Friends, during this tutorial, we shall study the Faraday's experiment and the right hand rule to find the polarity of the field produced in the coil. Then analyze the results of Faraday's experiment by applying Lenz's law. Finally, let us state the Faraday's law of electromagnetic induction. Friends, Faraday, as a first step, moved the magnet and for a moment he was surprised. When the magnet was moved towards the coil, the current in the coil was present and the deflection of the galvanometer was on one side as seen. But it was interesting to note that when the magnet became stationary, the pointer came back to zero. Further, when the magnet was moved away from the coil, the current in the coil was found to reverse and the deflection of the galvanometer was on the other side as seen. But again, when the magnet became stationary, the pointer came back to zero, meaning he concluded that the current in the coil or the induced EMF is present in the coil only when the flux linking the coil is changing. Friends, Michael Faraday did not stop his experiment at this stage also and continued his experiment. This time, he moved the magnet towards the coil faster than the earlier speed and the deflection of the galvanometer was found to be more. And again, when the magnet became stationary, the pointer came back to zero. Further, when the magnet was moved away from the coil with the same higher speed, the deflection of the galvanometer pointer moved on the other side and the induced EMF was more. But again, when the magnet became stationary, the pointer came back to zero. He observed by increasing the speed more and more and concluded that the flux linkage will be more if the speed of the magnet is more, meaning as the speed of the magnet is increased, the flux linking the coil also will increase. Further, he took the coil of 2n, 3n turns and so on. Now also, the induced EMF was found to be more and more as the number of turns n was increasing more and more. When the coil was kept stationary and the magnet was moved, or the magnet was kept stationary and the coil was moved, the result was same. Friends, by analyzing the results, Michael Faraday concluded as 1. When the flux linking the coil changes, EMF is induced in the coil. The induced EMF is proportional to the rate of change of flux linkage. The induced EMF also is dependent on the relative motion between the coil and the magnet. The flux linkage is equal to N into 5 Weber turns and the rate of change of flux is equal to d5 by dt. Friends, now how about the direction of polarity of the field around the coil when the magnet is moving? To understand that, the right hand grip rule is used. Observe the figure shown. We saw that when the magnet was moved towards the coil, the direction of the current in the coil was in one direction. When the magnet was moved away from the coil, the direction of the current was reversed. Now, to apply the right hand grip rule, we should observe the direction of current in the coil and grip the coil such that the four fingers other than the thumb are bent as shown, so that they point in the direction of current in the coil. The thumb must be stretched straight horizontally as shown. Then the thumb will point towards the north pole of the field produced. Note that the flux direction is leaving the north pole as seen. Friends, now let us see what happens when the current in the coil is reversed as shown in figure. How to grip the coil is shown. You find that when the current in the coil is reversed, the direction of the north pole also is reversed. Note that. Next, we shall apply the right hand rule, analyze and understand the Lenz's law. Friends, we know that when the magnet is moved towards the coil, current will flow through the coil and it produces the magnetic flux as shown. We also know how to find the direction of the field produced by the coil current by applying right hand grip rule. The German physicist Heinrich Lenz studied this effect and in 1834 he announced the cause for this effect. According to Heinrich Lenz, the field produced by the coil will oppose the cause. Then, what is the cause opposing EMF induced in the coil? You know, it is the motion of the magnet. But how does the coil oppose the motion? Friends, when the north pole of the magnet is moved towards the coil produces north pole as shown. So there will be a repelling force produced by the coil field. Hence, the magnet is trying to move towards the coil and the field of the coil is trying to repel by producing the repelling force. But when the magnet is moved away from the coil, what happens? We shall see next. Friends, we know that when the magnet is moved away from the coil, current through the coil reverses and it produces the magnetic field as shown. It is seen that by applying the right hand grip rule, the south pole of the field produced by the coil is towards the north pole of the magnet. Hence, now also the field produced by the coil will oppose the cause, that is motion. How is that? The north pole of the magnet is trying to move away from the coil, but the south pole of the coil field is trying to pull it by producing the attractive force. Is it interesting? Therefore, friends, according to Faraday's law, induced EMF say E is equal to N into d phi by dt volts, but according to Lenz's law, E is equal to minus N into d phi by dt volts. Here, the negative sign indicates that the induced EMF opposes the cause. Note, the voltage E is not a negative voltage. Friends, visual learning is more effective and help retaining the information for a long time. Hope you enjoyed viewing. Thank you for watching.